Today's number seven out of 8, so we're almost at the end of this course. Please try to follow as best you can, and if you have any questions, ask. We have one more class after this, and then we have the midterm. Okay. So today we're going to dive more deeply into this value function approach to thinking about macroeconomics, and it's useful for many reasons. I tried to motivate it last time. I'll repeat some of that motivation today, and we'll proceed from that. We'll move from a linear quadratic approximation to a more general problem. Then we'll talk about the more general problem that you'll encounter in macroeconomics. In this section, we'll finish the spectral density discussion. I have posted the solutions already in advance, so the stuff that we'll talk about with respect to the new Keynesian Phillips curve will be in that handout, that solution set online right now. And then we'll maybe get to the Kagan model. If not, I'll just put it on the problem set, and that'll be part of the thing to look at, because it's really useful. It's a little bit like the Phillips curve problem. Just how do we mold and massage this model to make it look like the state space, and then we can use the state space tool to make forecasts and to solve it, all these things. Okay. So there's a midterm, you know that. It's kind of the final for my part of the course. We want you to take macro seriously instead of only working on micro. So Lutz and I agreed to separate our efforts. So it'll be easier than the final in the sense that it's doable, but it will test you and try to create variance in the outcome. The idea always with an exam is to find out who's prepared and who's smart, but maybe not so optimally prepared. And some people are smart and optimally prepared. And it's like taking logarithms. It's a way of stretching things out a little bit, and you can see the percentage deviations better. So you're allowed to use anything you want except electronic devices, and I will be very strict on that. Okay, I don't want people communicating or calling their grandmother for help. That's not allowed. I say that with a bit of irony because it has happened in the past. Okay, and we've had during the pandemic we had exams on Zoom, and it was a real pain. Okay, and I'd just like to be here and hold your hands if necessary, but we'll do it all together. Any questions about that? Yes?
Open book, as in we can take all of our notes.
You can take anything you want as long as it's on paper, okay? But no electronics, no computers. You don't need computers for this. Okay? Any other questions? Okay. Please be on time. Right. Excellent. Okay, so last week we had new applications of the state space. We discussed briefly the Kalman filter. We discussed this notion of a quadratic form, sort of like a sandwich of a state vector, some matrix, another and the state vector again, and it results in a scalar number, and you can think of that as like a utility function or profit function. You can take discounted values of that, so you have the kind of macro intertemporal optimization tool that we've been looking for, but linear quadratic. So it has first derivatives that are linear and has second derivatives that are constant. So it's really convenient in terms of thinking about just the intuition. It's a useful way of approximating more complicated problems, and it's often used just for that reason. And then I mentioned some things you can do with that, but most importantly, modeling expectations is the real value of the state space. We know that agents care about the future a lot, especially if they're patient, and when they do that, they really want to know. So we talk about the new Keynesian model later on today in the section. One of the interesting problems with that model is that people setting prices really care about the future, and if they think something is coming, they start changing their behavior on price setting today. So inflation can actually have a bit more volatile behavior than we actually see in the data. Only recently have we begun to think maybe this model isn't so bad after all, because we've had this big rise in inflation, and it's almost as if many producers were front-loading Okay, so you might think of that as a plus for the new Keynesian model. The problem is that there are other disadvantages of the new Keynesian model, that the way we think about firms setting prices, whether they have the right to do so, or whether there's some sort of random selection of people who are looking at the price decision at any point in time. These are all a bit ad hoc, and they're subject to the Lucas critique. So the big debate in macro is this the right model to think about inflation, given that inflation is such a problem right now? I mean, we have 10% in Germany, which is, for most Germans, is what their grandmothers talked about when they talked about hyperinflation, in their heads anyway. Of course, hyperinflation is much worse, but so it's an important thing to think about. That's why the state space is really an important tool for all the things you'll do in the future. So we learned that thinking about dynamic optimization, the first approach is doing a Lagrange multiplier approach with a sequence of constraints that are usually binding in every period, and then solving the model like that. The second is this value function approach, which simply consists of collapsing a infinite dimensional problem with respect to time into two periods. And the notion is that the optimization problem repeats itself in the next period in exactly the same way, although it's based on a different state of the world. It's a rule, it's a policy that we can maybe try to find. And then if we can do that, we can find the value of the optimized problem in the second period when the state has been realized, even though we don't know what that state is. And we might even be able to influence that state. Okay, so you need to have a return function. You need to have a problem set up that you're trying to maximize in a time-consistent way, so it'll be discounted values of this looking into the future. And I tried to make the argument that it's a little bit like the utility function, the indirect utility function in micro, which only depends on prices and your wealth or your income. It doesn't depend on the goods you're consuming. So it's already optimized out that decision. So in a little sense, in a certain way, the value function is kind of like that approach that we know from microeconomics. Okay, so I'm going to do exactly what we did last time for the first 5 minutes. I'm just going to repeat what we did, so you just, oh yeah, I remember that, we saw that. And then I'm going to show you how that thing sort of maps into a problem where you are anticipating, as the optimizer, your own optimal policy in the next period. You're optimizing, given that you know that in the next period you'll optimize again on the basis of things you've done today. So in a sense, you know you can influence your own state tomorrow in a well-defined way, mostly deterministic. So if you save, you have more money tomorrow, or if you build more capital stock today, you'll have more capital stock tomorrow. And that's the way you capture this. So this is first a very abstract way. We started with this alpha. This alpha is a present discounted value of some sequence of quadratic forms. Quadratic form is like a sandwich, x prime times a matrix times x, and it's a scalar valued object. And if you just take the present discounted value of many of those into the future, we can think of that as something you'd like to make as big as possible or make as small as possible. Okay, so often in monetary economics, the central banker might want to minimize the loss function, but not just today, but loss of the future. And that loss may be how far inflation is from her objective, her ideal, and how far output is from some ideal, the output gap, for example. And then you just discount that back. But you know that if you raise interest rates today, you affect the economy tomorrow, and then you have to sort of make sure you get that right. And getting that right means understanding this problem. And if it's linear quadratic, it's pretty easy to follow. So think of Y as a weighting matrix that defines my utility or my profits or whatever I'm maximizing, and it's fixed. It has a lot of economic interpretation. It might be a linearized version of a much more complicated problem. And we're just looking at small deviations around that problem. Okay, and we know that if we can influence somehow the path of xt, and remember xt is the state defined Lundquist and Sargent way. It's the list of all the variables we're tracking. Some of them may be predetermined, some of them may be the control that we care about. And we may care about the control in two ways. First, it affects the state, and the state affects our utility, but it also may be affecting us directly. So we may get utility from consumption, and consumption could also affect future capital stocks, right? So you need to just, the economics is starting to come through, maybe only slowly. It's a very arcane type of setup, but last week we used the guess and verify approach, which is classic in macro. If you know the model's linear or linear quadratic and the solution has linear quadratic form, you can guess and be pretty much sure that the policy will be linear, and then you can try to figure out what it is using the structure of the model that we already know. Okay, so that's what we did last time. We wrote this down, and we said, hey, okay, well, let's just assume that the value function alpha t looks like the left-hand side, but if it does, then I should be able to plug it into the right-hand side since it is optimal, right? And they should be identical. But alpha t plus 1 is exactly the right-hand side leaded by one period. So if you look carefully at the right-hand side, you've got the return function in period t, and you've got the expected value conditional on t information of the rest of my utility, which by assumption looks like this, if I'm doing the right thing. Right? So in a sense, if alpha defines optimal policy, then I can solve this thing forward. Even if it doesn't define optimal policy, whatever it is, we can solve for this. And the equivalence of the left and the right-hand side mean that I can take that last step. Okay, moving from here to here. And then, of course, I can use the tools we've learned, expectation conditional on period t information of something in the next period. And that's where, and of course, sigma is a constant. So the assumed form of the value function is a quadratic form plus a constant, a shift term that raises or lowers the thing, and it's time invariant, state invariant. Okay? So the next is just application of all the steps that we've done in many different cases. We multiply out this quadratic form, you get 4 terms. You can take expectations of those 4 terms plus the sigma. Sigma is a constant anyway. Everything else is, they're scalars by construction. But you can see there's kind of an interesting pattern here in a lot of these macroeconomics problems. Omega is a mean zero orthogonal piece of information that we get in t plus 1. We're not going to know what it is in period t, and our expectation of it is going to be equal to 0 when it's multiplied by things that are in the information set in period t. So the second and the third terms disappear. The first term is a constant, and the last term is a constant. But we have to evaluate it. That last term we evaluated last time using the this trace operator property, which I'll talk about in a second. But does everyone understand that the movement from the second to the last step? We've just multiplied it out. But the most important thing you should notice is that although the original problem had expectations of xt plus I into the future, I greater than 0, we've eliminated it. Now we only have basically things that are a function of t plus 1. So it's already a 2-period problem. That's the logic of the value function approach. And you can see already that the first term, the leading term on the right-hand side, is a function only of xt. It's a quadratic form, just like the left-hand side. Okay, known information in period t. And that's just because we use the period t information to forecast the future, and the quadratic form and the assumed form of the value function allows us to do that. The only thing we have to do is evaluate this nasty-looking element. It's nothing but a vector product of a random a random vector with itself, but it's sandwiched with this stuff, so it's weighted. And it's not obvious how to evaluate that, but it turns out that you can. Using this result in econometrics, it says that if you have a square matrix, the trace of AB is equal to BA. So if AB is square, it could be it could be an outer product of just a conformable vector with its transposer. It could be A and B could be matrices. This is just a result that we know from Helmut Lütkepohl and Henri Theil. Okay, so we can rewrite that The left-hand side can be rewritten just by applying this matrix result. And when we do that, we basically have the expectation, which we can pass through a bunch of constants, because C is a constant, is a matrix of constants, and V is a matrix of constants. And what's inside is this is exactly the covariance matrix of omega t plus 1. And under the assumptions we've made, that thing is equal to the identity matrix, and therefore what's left is the trace of this V matrix times C transpose, and that's a 1 by 1. Okay, so actually we can now write the result in matched terms. The left-hand side, you can see, is a quadratic form in xt, and the right-hand side is a quadratic form in xt. Those terms we can match, and we can also match sigma on the left-hand side with beta times this trace and beta times sigma. Okay, so we start with V, because V is a matrix. We have to solve for it. Kind of not something you do on the final exam, but you should know that it's not impossible to do this. In fact, under pretty general conditions, it will have a unique solution. You can use iteration to solve for it, or you can just go online and find a program that will do this for you. Okay, or even Sargent's website has this program. Okay, so once you do that, once you find out what V is a matrix that's going to be encapsulating remember, V is the central matrix in the alpha function. So once we have that, then we can actually find the value, the quadratic, present discounted value of this quadratic form. We still don't have the level yet, because we don't know what sigma is. You can solve for sigma just by using the formula and just solving. It's a linear function of the trace of this matrix, and that you can do as well. Remember, the trace is just the sum of the diagonal elements. These are always square matrices. So that's just a mathematical result, but if you thought of it before, if alpha were actually a value function, then this would be the way of solving for it. Okay? If we're talking about optimal policy, this is a way of interpreting alpha. Otherwise, it's just a quadratic form. We just try to solve for it using the value, using the guess and verify approach. Okay, so now I'm going to try to make you believe that it actually could be a value function if the state vector incorporates optimal behavior. Okay, this is also in Lundquist and Sargent chapter 3, and I apologize for if the reading list wasn't completely visible to you, but it is now. And I know you've been following in chapter 2 and 3, so it's not a disaster, but I do apologize for that. Okay, so suppose, and I'm using their notation, so it's really simple. If the state is influenced by U, okay, it doesn't change anything, but it just has a different interpretation to this component of some part of xt is influenced by U in the following way. So think of that equation as being a way of summarizing how I could affect, by changing U, a control vector. So think of U as a vector of, could be a single consumption today. It could be consumption and investment today. It could be a bunch of other things. And in my actions today, I can affect xt plus 1. So we say that the state vector is in some sense controllable. I can influence it. Then you can actually just plug in that into plug in this policy into UT, and because UT is conditioned on the state, that's the assumption. I can only look at the current state, and I can take decisions. That's my policy rule. F is the way of thinking of this policy rule. Then basically we collapse it into the same state space representation we had originally. So if you're wondering why did Lundquist and Sargent and the older books use A0, it's because they start with this more general form, and they have B as the controllable part of the evolution of xt, and then they just fold it into this value. So then we have AOC. Remember last time I talked about AOC? This is AOC, okay? So if indeed, under these conditions, if F0 is really optimal policy in the linear quadratic sense, then indeed our form that we just derived is optimal policy. It is the value function, right? Because you're doing the best you can, because we've assumed that B is that F is the summary of the steering of this problem in an optimal fashion. Okay, so this is to get you ready, because now we're going to try to solve for F. We're going to actually try to solve for it. Okay. So before I go any further, let's try to collect our thoughts. Think of U, this F times the state is like an optimal policy, and it implies a value function. So you tell me what your optimal policy is, I can put it into the objective, and by definition, that is the value function. Conversely, if you tell me what the value function is, I can infer optimal policy from it. Why is that? Well, I can use the two-period approach. I can plug in the putative optimized value function and then derive the policy that I would choose, given that I can influence the state in the future, and I know what this value function is going to be. That will also have to be optimal policy. So it's like a bidirectional, unique assignment. Value function implies an optimal policy. An optimal policy defines a value function. We'll do this in a second. We'll show this. And this is basically what the Bellman equation tells us. The Bellman equation defines the value function in terms of the best you can do, given that you have, so to speak, one chance to affect today's control, and by influencing tomorrow's state, you influence tomorrow's value. So I've collapsed effectively this infinite time horizon problem into two periods. This is why the book is called Recursive Macroeconomic Theory. Basically, this is the basic idea of the entire book. When we get this intuition down, we'll extend it to a nonlinear quadratic setup. Okay? You guys with me? You look a bit skeptical, that's fine. Okay, so let's define now. Let's do this properly. Let's start with a return function. We call this usually for the household, it might be the utility function. The periodic utility function. So the utility of the household is not just today's utility, but it's tomorrow's and the next, and we weight them using discounting. And this is a general way that allows us to get a scalar out of the things that constitute the state and the things that constitute our control of the state. Okay, so the control of the state, and again, this is, as we saw, tomorrow's state. You can't control today's state, but you may have utility over today's control, which would be summarized by Q. Remember, Q is a square matrix. It takes these two vectors, the transpose and the vector itself, and creates a scalar out of it. So then you can think of this as utility of, if U is consumption, then I might also get utility from owning a piece of the capital stock. It's not the way we usually do it, but it's general. So you might actually get utility from the state, but you don't have to. So if R is equal to, you set R equal to 0, then you're just basically considering your direct control over utility through your choice of consumption. But you do affect the capital stock, which does affect your potential for consuming tomorrow. So you can't eliminate the role that the capital will have in your utility that you maximize. But we'll keep this sufficiently general. So R is a non-trivial matrix that creates the quadratic form, square matrix, and Q applied to the controls. Okay, so in this particular case, again, following the notation in the book, just in case you want to go back and check, this is basically allowing us to keep a max. This problem is formulated for a minimum loss. Okay, so minus of a minus gives a plus. So we're going to keep this a maximization problem, just like Lundquist and Sargent do. So the problem will look like this. It'll have a minus sign in front. It'll be a present discounted value of this return function using beta as a discount factor from t equals 0 to infinity. Now this is the primal problem. It's like duality theory in micro. Right? You're going back and forth. We're going to go from this infinite time horizon problem to sort of the dual, which would be kind of the value function approach. Okay, so we're going to, again, suppose that the agent maximizing solving this problem, maximizing this, chooses optimal policy, and it's given by this f. That's the basic solution to this problem. We want to find f now. I'm going to try to motivate how to get to f in this problem. But first, let's just try to make sure we understand that everything we did in the last 10, 15 minutes maps into this problem. So the value function looks like this. I've plugged in assuming that the policy is achieved by maximum optimizing behavior, which gave us f. You just plug in f for to illustrate the control over the state. So you end up having this new quadratic form, which has instead in the sandwich, the interior of the sandwich of the quadratic form, it has r plus f prime times q times f. So it's conformable, it's got the right dimensions, it's n by n. And we know from what we just learned is that if this thing has a unique solver, then it's going to take the form given by this expression, just like before. And the Bellman equation would be simply solving this problem. I'm choosing the policy controls u0 in time 0 to maximize this object, given that this value is optimized and therefore is the same thing as the object on the right-hand side. So that's the Bellman equation in this particular example. Okay, so we've got scalar on the left, scalar on the right. It's very similar to what we had before. It's identical to what we had before. So we already know we know how to solve this. And we can use guess and verify to solve this. But to do it properly, we need to specify the constraint because it's not completely unconstrained, this problem. We're choosing u, but we have a constraint. And the constraint is our influence over the state tomorrow. So think of if xt contains the capital stock tomorrow, I influence the capital stock tomorrow by investing a lot today. I can't change the capital stock today, but I can change it tomorrow. So that's one example of this very general formulation. There are lots of other things that could be in there, right? Okay, so that's the completely specified Bellman equation for the linear quadratic case. Any questions about that? Now, I'm repeating this. I repeated the beginning of the lecture, what we did last time, just to make sure now you understand there is this transition. You know, before it was just matrix manipulation. Now it actually has an interpretation. So we can solve for this optimal policy vector, or by finding f. We know that f, by the definition of the Bellman equation, has to satisfy that. Now we just have to find it, right? But it's a two-period problem now. I'm choosing u, this list of controls, today, period 0, to make that object as big as possible, given my constraint. Okay, so if you just take the last line and insert it into the right-hand side, the third term, you can see that's my influence. I mean, basically, when I do something, I have a benefit today, and I have some cost expressed tomorrow, or some benefit tomorrow expressed in cost today. Okay, that's basically the intuition behind this equation. So the first order conditions will be basically choosing u to make that object as big as possible. But it's a two-period object. It's today and the best I can do tomorrow, given what I can do to tomorrow's state vector today. So it looks like it's a very simple setup, especially if we reduce it to a scalar form, it makes perfect sense. But it's basically a weighting of all the influences I have on both the current return function and the future value of the state, given that I can influence it tomorrow. Okay, so you can just solve this matrix expression and get the matrix F that we postulated was optimal policy. Okay, F depends on Q, it depends on B, it depends on beta, obviously, and patience, and P is not necessarily the same P that's implied by F. So we have to make those two conformable or consistent with each other. So, we start this problem. If we wanted to actually get it, we'd have to know what P is. But P is implied by F. So we can guess P and see what F is implied by that, and then we can reiterate and see if we get closer to some steady, unchanging value of F. And if we can do that, if we have a computer, okay, that's the last 50 years have made it very easy to solve this problem in milliseconds. All we have to do is just define some tolerance that this iteration results in a value of F that doesn't change anymore. And that's going to be a characterization of optimal policy. So this is you say, well, what happened to the calculus? Well, the calculus gave us the optimal behavior given P, but we have to get P. And if we don't know what P is, we're going to have to maybe guess it or maybe take an initial guess. This is called Howard's improvement algorithm. So it's kind of one of these crazy things that come out of physics and engineering that economists have used in a very constructive way. So you start with a guess of the policy rule, and then you use that policy rule to compute the P matrix, and then you repeat. And you keep doing that basically until F doesn't change very much. So the J superscripts are just the number of iterations you're performing, or you have performed up until that point. So it's a recursive problem. And you're trying to make this either the objective, the policy function, or the P matrix converge to something. So this is a commonly used technique. If you give me a problem and I put it in linear quadratic form, then you can solve for the analog problem of a linear quadratic decision maker trying to minimize or maximize something, maximize in this case, this present discounted sum of quadratic forms. Okay? So now, given Howard, we can generalize this. So, the Howard improvement algorithm is a way of doing this in the linear quadratic setup, gives very, very clear marching orders how to solve this, but we can generalize this dynamic approach, otherwise it wouldn't be maybe that interesting to you. As I told you already, if I had done this on my thesis, I would have saved several weeks of work, because these problems are quite easy to solve when you do it that way. But we're more interested in solving modern problems, the new Keynesian price setter, or the household trying to smooth consumption over time, the firm investing in capital when there are adjustment costs. All these types of problems are ones that come up. So they're all kind of they can always be kind of expressed if the functions involved are continuous. We can take linear approximations, quadratic approximations, and then we can write this in terms of the so-called linear regulator problem. But the most important thing to remember from this discussion is the intuition. You start with a policy rule. It implies a value function because the policy is optimal behavior. The value function is the optimized value of the problem you're trying to solve, the maximization problem. And given the putative form of the value function, we can actually derive the policy function from that, which is depending on the state, right? So it's but this is a more general thing. Okay, so we're going to think about a more general statement. And this is also in the book. We're going to use the same notation. We're going to use U as the policy, the choice. So it could be a scalar, it could be a vector. In macro, it's usually a vector of problems or controls. Think of the household choosing not just consumption of non-durables, but also durables. And durables are like a capital stock. When you buy a refrigerator, you don't just eat it. You keep it for like 10 years, and it's still around, and it depreciates. So this is a great problem to start with. Think about that. And many people have gotten very famous thinking about those kind of problems. And you can have central bankers choosing, interest rate, open market operations, list of policy. Then you have different return, different influences on the state of the economy that the central banker cares about. And we write them basically in terms of this R. So R is like a general function that translates the state today and the controls today into some utility today or profit today or welfare, whatever. Okay, and so note we're already buried important assumptions in this problem. What have we assumed here? Just for make sure you're paying attention. We talked about it last week. When you write down an optimization problem like that, or an objective like that, you want to maximize that. What are we presuming? We're presuming that it's not necessarily time separable, but we can write it in this form. It's the sum of evaluations of the state in every period. We've ruled out a lot of time inconsistent behavior. Remember we talked about addiction, talked about hyperbolic discounting. So a lot of these things have been kind of ruled out by this. I'm just trying to be honest with you. But this is where we look. This is the light post that we're looking under these days, because it does work for a lot of problems. But you should be aware that we've already narrowed our vision, and this is kind of the classic setup. Okay, so we have the return function defined over x and u in period t. And again, if you have imagination, you can plug in lagged values of x, of the state. You can make the state vector very long like we did before. You just have to do it right in a way that's consistent with this setup. Okay, so you're allowed to have utility over the past, but it has to be utility over the past in a certain consistent, time-consistent way. So habit formation is okay. You can put it in here, but there's some formulations are not allowed. So you have to press it into this box. And this is the constraint. So you can't just take anything and maximize it. You have to obey some rules. The budget constraint, resource constraint, and these are summarized very generally, and they've got a stochastic element. So it's a potentially nonlinear function of these objects. Okay, so G is basically expressing the set of things that I can do, I can get away with. Think of it as the budget constraint. I can't produce with capital that I don't have. I can't get utility from refrigerators I don't own. Okay, so that's the way it is, and that depends on the state. It depends on my controls today, and it depends on this randomness. So the randomness might make us suddenly richer or poor, but in ways that we can't anticipate and we can't control. It's really uncontrollable. And xt is just this vector of my possible outcomes that I care about. I mean, I obviously have this utility over xt, and it's evolving over time, but I can influence it, and this is supposed to subsume that. This is a pretty general setup. Okay, it's pretty general, and the inequality is usually replaced by an equality. Think about it. If you have resources that you can use and they're valuable to you, only if you're satiated would you toss them into the garbage. So in all the practical applications we'll set the inequality, the weak inequality into an equality. So now, does this problem even have a value function representation? So that's the question that Lucas and Stokey and Ed Prescott was also involved in this book. finding the mathematical conditions, the sufficient conditions. Okay, it turns out they're not necessary. You can cook up some problems that also have a value function representation, but they don't fulfill this. But if you can fulfill these properties, you know that you got it. And they're kind of strict, actually. So one is that this return function is bounded. Now, one of the most popular examples in macro that we use is the log function. The log function is not bounded, but the log function works. Okay, so it's like we're groping a little bit in the dark, but if you can write down a problem with a strictly bounded value return function R, then you will meet the sufficient conditions for finding a unique value function in this problem. The second set of conditions is more relevant for us. It's basically that you don't have non-convexities in the problem. So what's the biggest non-convexity we have in economics? What's the most disturbing for you? I mean, it's a personal question, but in economics, what disturbs you the most? Non-convexities. Does everybody remember what a convexity is? What the property of convexity is? You probably remember that. If you want to explain it to your grandmother, what do you say? If a set is convex, yeah. You're close. A mixture is in the set. A linear combination of 2 points in the set are in the set, always. Okay, and closed means the boundaries are also in the set. So that's kind of, you need that. And a non-convexity means you might have increasing returns to scale. That's one thing that really gets economists going. Right? Increasing return to scale, if I get bigger, I get more productive, I can consume more. You know, it's the antithesis of the competitive model. It wrecks the first welfare theorem or the second welfare theorem. It kind of disturbs us, right? It leads to monopolies, right? Amazon, think about it. Google. Okay, so we're kind of digging a hole right now, but it's true. To get this to work, we need to have a convex set and not a non-convex set. And we have to, of course, have this stochastic process behave in a way that we understand. So I said these are necessary but not sufficient, sufficient but not necessary conditions, and you can actually cook a problem. The one we'll use later as an example, the log function with Cobb-Douglas production. It works. Okay, and actually there's a unique value function representation of a dynamic optimization problem for the household. That works, but we don't have a theorem that tells us that that works. Okay, if we have these conditions, we can write down an optimal policy rule that satisfies this Bellman equation. Okay, so this is the policy rule that is the maximizer of this two-period problem that makes recourse to itself. So V is the value function defined on the state, and it's the sum of two things. It's the maximized sum of two things. One is the value today of the return function, and the other is the expected discounted future value of the problem, the value function, evaluated at tomorrow's state. So note carefully. Why is that not t plus 1? Because xt plus 1 is defined by g of xt, ut, and this randomness. Okay, so this incorporates the ultimate control I have over my own future today, both by influencing my utility of x today, but also by influencing x tomorrow through the g function. So again, a very general formulation. Most problems that we'll deal with in macro can be pushed and squeezed into this form if we appropriately define the state vector. This is the Bellman equation. And what makes this Bellman equation so interesting is that V on the left-hand side is the V on the right-hand side. And V is the best I can do, given my environment, given my restrictions, my constraints, and given my information set today. Okay, this is a very powerful result. So powerful that we spend a little bit of time talking about it. And once you finish this course, you won't talk about it again unless you really want to. But if you're going to do micro, for example, I'd consider thinking about it. A lot of dynamic games are involving exactly this kind of problem. You know, I'm investing in a reputation, for example. How do playing one-on-one with somebody, trying to scare somebody, create some sort of image or something. I don't know. So more generally, this is just to be honest. You can do this even when Lucas and Stokey aren't right. I mean, this is just a definition of what a value function is. The best I do today is what I can influence my utility today, plus my influence over my valuation tomorrow, which may not be the same function. So in the more general case, you have a subscript here. This function is not the same function. You could have a time-dependent value function. Those are more worrisome and characteristic of non-stationary environments, for example, or maybe changing tastes. Maybe I get more patient as I get older. All these things are time-dependent. This is a more difficult situation. It's also kind of a Bellman equation, but those functions aren't the same, so a lot of the tricks I'm going to use don't apply. So, but I'm going to characterize the value function in the Bellman equation case where v on the left and right-hand side are the same function. Okay, so there's our hero of the day. Okay, he's the guy that invented this. And if you don't get the intuition, just read this sentence. Okay, so in a sense, you're making this plan, and you know that you're influencing your tomorrow's state of the world, and it better be the case that you're thinking about that when you take your decision today, because you're actually influencing where you're going to be tomorrow. Okay, so that's the logic of Bellman. There are 4 results that we need to keep in mind, because this is going to help us make the translation and the mental correspondence between the dynamic programming approach and the Lagrange approach that we already did. Because it turns out that if you do it the Lagrange way, you get the same answer, but you have to deal with this idea of, at least at the optimum, we have an infinite sequence of first order conditions and a transversality condition or some sort of boundary condition. And with the DP approach, you've cooked it to a two-period problem, doing the best you can given your influence on tomorrow's state vector. So if you get the value function, if you're in a situation where the value function characterizes this problem you've looked at, then, and again, assuming the things we've assumed, that the return function is concave, that the set defined by the transition equations for the state is convex, that is, there are no non-convexities in that set, then we can say with confidence that the V function, first it's unique, there's a single function that represents this problem's maximum, and it's differentiable, and it's concave. So the first result says it's concave. You can take derivatives of this function. You can solve it by iteration. And this is an important result in that book. This is what's called a contraction mapping. So you're basically you're starting with one function, you put it into this machine on the right, and you get a new function. And the unique solution is when the function you started with is extremely close to the one you end up with, in a mathematical sense. Two functions you can think of a difference between two functions, the maximum distance between the two. This is that result. So we can start with a guess, and if we have the capacity and the will and the patience and maybe a computer, we can actually get very, very close, just as we did before with the linear quadratic case, to the true value function. Okay, so you just have to solve this. Again, and do it a number of times. So you can guess, you can literally guess a form. You can do all sorts of numerical representations of V and just carry those through after you've done the optimization and adjust your values of V, which is a function now. It depends on the state vector. And do that often enough and we can actually converge. Okay, so we've got a policy function that's defined by V. So if we get V, we can solve for H because H is the maximizer of that same problem. Okay, but you just have to write down the first order conditions and characterize that optimal policy. So that's going back to what we had before. And the last result, this function is differentiable. So at all points on this state vector, we can take the derivative of this function and we can write it like this. It's the sum of two parts. It's the sum of the state's influence on today's return. That's the first component. And the second is the induced effect on tomorrow's state by changing today's state. Okay, so you're going to have a discounting effect. And this expectation is a conditional expectation taken over information in period 0. And it looks like this. So this looks a little bit like the envelope theorem of microeconomics. Remember the envelope theorem? If you're doing the right thing, you change the price a little bit, you can evaluate your utility, your maximized utility, without looking at the responsive quantities. That's the envelope theorem. So it's a little bit like the envelope theorem. Right? So this characterizes optimal behavior. Because what is V prime X on the left-hand side? It's like saying, okay, there are parts of the state that I can't change. Right? Like I can't change the capital stock today, but if I could change it, what would it be worth to me? It would be the value, my optimized value, incremented by the fact that I have a little bit more capital to produce with today. Even though I can't get it from the shelf, that value, that shadow value, is exactly the same interpretation that we had before of the Lagrange multiplier. And the Lagrange multiplier has to have a certain path as it goes through time, and that's going to be defined by the right-hand side. Okay, so that's called the Benveniste-Schenkman equation. Jose Schenkman, famous theorist at Chicago. Think of it as the change on the left-hand side, the value of changing the state vector a little bit, given that I'm behaving optimally on the left-hand side, and the right-hand side decomposes it into the two parts. Okay, one is the direct effect on my utility today or my profits today, and the other is the induced effect on the state tomorrow, without recourse or regard to the possible change in plans that I might want to take. Those are equal to 0. Okay? So, how to solve these problems in practice? One is suggested by those 4 results. One is called value function iteration. So I give you a complicated problem. If you're willing to wait and iterate long enough, you will converge to something that you can use. And it won't have a closed form representation, but you can plot it. So a lot of what we see in economics is plotting the value function as a function of states. And if you have one state, you can plot it as a function of one state. If you have 2 states, then you have to freeze one state and look at the variation of the other. 2-dimensional, so it's a problem with visualization. We also talked about the second possibility already, which is to iterate on the policy function. We called it Howard's improvement algorithm. And we already talked about the other one, which was guess and verify. So I know what the value function looks like in advance. If I have a pretty good idea, theory would suggest, or maybe practice has suggested that it's going to be a linear quadratic. I'm dealing with a linear quadratic as an objective anyway, then I can pretty much be assured. Then I can use guess and verify to get the answer. Okay, so those are kind of the 3 possibilities. So this is kind of bad news for those of you who like to see a closed form, neat, something we can write down and show to our friends, say, I got an answer here. So when I was doing my PhD, linear quadratic was the way to do that because you get linear quadratic problems that give you linear policy rules, and you can write down a value function. I think I told you already about what I was working on. So it's kind of it's very satisfying, but maybe for large changes not so good, and you probably care about other aspects of the solution. So approximation is probably not the way to go. So these are ways to do it. The value function iteration approach would be, like I said, a representation. You'd have a grid of the state vector that you're interested in, and then you could look at the way this function, by iteration, you can solve for the value function at each point on the grid, and if you reach that convergence of the value function, you can actually, like I said, you can plot it or you can evaluate it. It's doable. So that slide with the value function iteration defines the way of approaching this, right? So you have a function that you start with, and you apply the optimization, this two-period optimization. One time, get an answer, plot it, look at it. Is it very far from the initial guess? Yes, probably. We have to repeat, and sometimes it takes many, many iterations. So I've had some PhD students who've used this to tackle fairly difficult, nonlinear, but still well-behaved problems. Okay, so it's doable and requires a little bit of programming talent. Then you can do the Howard's improvement algorithm, which we talked about in the linear quadratic case. This is the more general sort of repetition of that problem in terms of j and j plus 1. So you start with an initial policy guess. That's why it's called policy function iteration. You start with a policy function. It induces a p, okay, which is the implied value function matrix that flows from your guess f. And then you can re-optimize, find the new f implied by that p, and is it consistent with your initial guess? Is it far away or close? So you're looking at the distance between the vector, the policy vector, and the j plus ith iteration compared to what you started with. This tends to converge more rapidly. And we already talked about guess and verify many times. So that's a kind of a classic approach, especially if you log linearize your macro model. Then this is the way to go, because if it's linear, the solution will be linear. Okay, so it's just a simple matrix operation on these very large state space systems. And that's what you'll be doing. That's what Dynar does for you, effectively. Okay, so that's you end up having, it's still not trivial, you end up having to find what's called the equation of motion of the system, which is this, you get rid of all the expectations of the future, and you have this sort of like this, you're pushing this big rock, and the rock is the state, the set of state variables that are not influenceable, but conditioned on them, they imply a certain behavior, which implies a certain dynamic for the state vector. So this equation of motion can be written in the same sort of form. Okay. So I wanted to give you an example of playing with this. This is kind of something that people still play with a lot, although there's a lot of unsatisfactory aspects of the CAPM model. So we already talked about what the household should do if the household has variable income and has access to a vehicle for saving. Well, you can extend this to think about uncertain returns. Because remember, in our example we dealt with, the interest rate was constant. It was pretty basic, but it had some pretty interesting implications. Remember, the marginal utility follows a martingale, and the person involved is trying to do the best she can by consuming on the basis of permanent income. That was the classic result. So we can generalize this, and this goes back to Paul Samuelson and Breeden and Merton, and Lucas wrote this very famous paper in '78 that's still quoted a lot, which is to take this theory of optimal consumer behavior and to turn it on its head and try to figure out how assets would behave in a world like that. Okay, so because people want to preserve their a smooth utility path. So if you invest in really risky assets, then the implied utility is probably very highly variable because the consumption from that asset might be very variable, but you might be giving up on something, which is the rate of return. So there's a rate of return risk trade-off. That's a very common idea that goes way back. So if you want to get the high return, you're going to have to accept some risk. And it turns out that the simple linear quadratic consumption model we dealt with in lecture 4 was really just about knowing the rate of return with certainty. So it's we can do better than that. So let's think about a household. Let's think about a finite period problem, make it even more easy for us. Okay, so we have a finite number of periods in this problem, so t, and after period t minus 1, you don't have any interest at all in this problem. So you probably want to make sure that you consume all your assets. There's no motive for leaving bequests or anything else. So you've got this dynamic equation now. AT in this problem is it's not a matrix anymore. It's a number. So it's your wealth. And your wealth is basically what you save from your income and assets last period, and you can invest them in two different possibilities and two different assets. So your total assets can be invested either in a risky asset or a less risky asset. Right now, I'll just keep them both potentially risky, so we can basically make the problem even more general to start with. So you'll see that it all depends on which one's riskier. And we have labor income too, but the labor income is known today, so it's not going to be a big important part of this problem. So we can write down a value function as simply maximizing utility in this particular situation, and it would be defined as the choice of my path of consumption, the path of my assets that I allocate, and again, if you don't allocate it in one asset, you've allocated it in the other, and then you've got the implied future path of A going forward, so it's using S as the index, going from T to T, cap T minus 1, of the utility that's implied by my policy. So you can see that it's already a complicated problem. I'm choosing my consumption. It's a plan. It's not like the Hall problem yet, because we had infinite horizon, and we also had a much simpler asset allocation problem. But I still have to choose this policy, okay? And for every period, I've got this evolution of my total financial assets. Okay, so you can rewrite this value on the left-hand side as the following on the right-hand side, knowing that I'm going to do the same thing in the next period, but no, we have a t plus 1 subscript. So it's a value function of the state of my asset holdings in t plus 1, but it's not the same function as vt. Okay, this looks like a difficult problem. The cool thing about this problem is it's finite. I know I'm going to be finished in period cap t. Okay? So in effect, we've written this problem. Importantly, we've written this this t-dimensional problem in a two-dimensional way. We've reduced it by the value function substitution. That's the big step. Okay, and the question is it useful to us? Is it going to be useful to us in getting a characterization of optimal behavior or of optimal allocation of portfolio wealth that is independent of V? Ultimately, we want to use V as like a crutch to help us to get some implications on the things we can observe, because we can't observe the value function of our agent. We just know the agent's optimizing. And of course, AT is given. In every period, you only have as much wealth as you can allocate, right? Does everybody follow? It's a pretty standard problem. 2 first-order conditions in each period T, not cap T. Right? So you can solve the problem we did before in its original form using Lagrange multipliers, and you can actually get a similar set, and they are ultimately identical in their implications, but we've reduced it to a 2-period problem. So how much do I allocate? How much do I consume? Given that in the next period I have a new optimal policy and a new optimal evaluation of my utility going forward, and I can influence that. That's why there's a derivative there, because there's a single argument to the value function, which is my wealth. Okay, so again, we have a nice interpretation of this, right? The marginal value to my optimized utility in period T of an additional unit of wealth is equal to the discounted value of the expected utility of that same marginal increase in AT's effect on value tomorrow. Why? Because if I get a little bit more wealth tomorrow, it's allocated in a way that it's basically going to be based on the returns of the 2 assets I'm holding. I'm holding 1 minus omega in the low risk asset and omega in the high risk asset. Okay, so that's the indifference I'm going to have, because if I get more wealth, what's it worth to me tomorrow? At the optimum, it's worth the first derivative of the value function tomorrow. Yeah.
Could you say with respect to what are the first order conditions? The first one is with respect to C?
Yeah, the first one is with respect to C, and the second one is with respect to AT plus 1. Because, and again, you have to obey the constraint, obviously. So when you plug in the constraint, this comes back. Yeah. And the second first order condition may be unfamiliar to some of you, but it's basically saying that at the mean, it's not at the mean, but the expected return times the value of that expected return should not be positive in expectation. So the value of allocating more portfolio wealth to the risky asset as opposed to the less risky asset should not give me any extra expected utility. And if it may give me more return, but it may make me less comfortable with that excess return. So in some sense, I'm not going to choose to do any more of that allocation, and that's implicitly defining the omega allocation between those 2 assets. So that's kind of hinting that just looking at expected values is not enough in this problem, because margin utility is decreasing at the margin. Okay, if you look at the left-hand side and the right-hand side, you actually noticed that the right-hand side is the first order condition number 1. So in other words, the margin utility of wealth is also equal to the margin utility of consumption today. So we can eliminate the first derivative of the value function today. So that's kind of neat. We were able to do that. And if you can do that today, you should be able to do it tomorrow as well, right? The expected value of margin utility at CT plus 1 should be the expected value of the value function differentiate with respect to the assets, the state variable tomorrow. So therefore, I can also do the same substitution in the second period. Okay? So doing that basically allows me to eliminate completely the value function from the first order condition. Okay, so it's kind of like, this is what we call an Euler equation for an economy with two assets. And think of this as the gross return on the portfolio, and it's a random variable in t+1. So we don't know what it's going to be. All we can do is control our exposure to it, which is omega. So we now have a problem with an intertemporal Euler equation like we had before with Hall-Friedman. We also have a portfolio choice problem. Okay, so the neat thing about this, this consumption CAP-M model is that if you have a fixed supply of assets in any period, an equilibrium has to make people happy to do what they do, and therefore this can actually define the rates of return structure in an economy like this. So it's like supply demand, supply is fixed, demand is variable, then we can derive the price by looking at the variability of demand given the supply. So that's kind of what Lucas did in his 78 paper. It was a tree economy. The tree is growing, throws fruits off. How much are you willing to pay for the tree? You don't know how much fruit you're going to get next year, so how much do you pay for it? That implies an expected rate of return. Okay, so we can, suppose, so now I'm going to make RT known. So suppose we know RT plus 1. It's like a guaranteed government bond. The United States has these inflation protected bonds where you get basically the CPI. So you always get a real rate of interest. You can back out, the French have it too, so you can actually back out the real interest rate by looking at it. That would be a real interest rate. If you do that, if you know what RT plus 1 is, it's kind of in the information set in period T, then you can factor it out, and you can basically derive this riskless rate by looking at the expected marginal rate of substitution, which is exactly what this is. This is known, so we can factor the expectations operator. We can't factor it out. We can't factor it out well, actually, since RT is known, we can actually bring it to the left-hand side, and we can actually solve for the real interest rate as a function of the known marginal rate of substitution, because you're planning your policy CT for every state of the world in CT plus 1, and the expectation of that would give you the value of the so-called riskless rate of return. And the risky rate of return satisfies the other condition. Okay, so that's one application of this very powerful tool. And notice we didn't even we just said the value function exists and it's unique. And given that, I was able to get rid of it because I could take the derivative of it and set those derivatives in the value function problem, and then I'm set to go. That's kind of a trick that people use when solving more complicated models. So again, if you're willing to allow me to assume that this one asset is riskless in the sense that I use the RT plus 1 because it pays off in T plus 1, but if we actually know what it is for sure, then it doesn't have any risk. We can factor it out, and we can solve for it. So in that case, the marginal rate of substitution in this model with stochastic stochastic assets leads to an expression for the marginal rate of substitution, which is directly related to the rate of return on the asset. Okay, so that's another implication of the theory. This is often called the stochastic discount factor. You'll see this in Lutz's part of the course. Okay. Now we don't have any capital in here, but we think the capital stock and the capital intensity of the physical capital is driving the marginal product of capital, and it's probably driving this interest rate. But this is a partial equilibrium model. So we're only looking at the agent facing these this random portfolio choice problem. But it's already very, very useful. So we're able to back out a relationship between in this case, the known rate of interest and the people's willingness to exchange consumption tomorrow for consumption today. So the Lucas was the first guy to do this. And you'll see this equation very often. When you introduce money, this will be related to the price level. You know, you have nominal interest rates as a setup. More generally, you can use this to price assets. So if PT plus 1 is the implied price of an asset that pays cap RT plus 1, then you can actually back out the price of assets, the risky asset today, PT, right? So the stock market is implied by this, right? You can, it's basically the